In this video, we're going to prove some theorems that come directly from the division algorithm. The first one is, if a is at least 1, actually it can be 1, and it's an integer, then a times a squared plus 1 is an integer. B, any integer of the form 6k plus 5 will be of the form 3j plus 2, but not conversely. We'll show that not conversely by a counterexample. If you square any integer, it will be of one of those two forms, 3k or 3k plus 1. If you cube any integer, it will be in the form of 9k, 9k plus 1, or 9k plus 8. The fourth power of any integer will be in the form of 5k or 5k plus 1. So let us go ahead and prove the first one. A times, is it a squared plus 2? A squared plus 2 divided by 3 is always an integer. Now, we can prove this by induction, but we won't. Now, either a is a multiple of 3, or a is a multiple of 3 remainder 1, or a multiple of 3 remainder 2. Each and every integer can be written that way. So, writing it in this form, 3k times, well, 3k squared is an integer, and when you add 2, it's an integer. And when you divide by 3, we see what we get. We get k times, I'll FOIL it out, 9 squared plus 2. This is an integer. If this is a, then you have a times a squared plus 2 divided by 3. 3 is not going to be reduced with 3k plus 1. In fact, other than 1, the only factor of 3 is 3. So 3 has to either go in here or in here. Squared. Well, this is 3k plus 1 times 9k squared plus 6k plus 1. But now I'll add the 2. 1 plus 2 is 3. Now, in that second factor, we certainly can pull out a 3. And we'll have 3k squared plus 2k plus 1. And then when we divide by 3, it goes in evenly. 3 goes into the numerator evenly. That is what I'm writing down right now is most definitely an integer. So now, a times a squared plus 2. That's supposed to be a multiple of 3. That's the only way 3 is going to go into it. Well, 3 doesn't go into 3k plus 2, but when we square that, we get 9k squared plus 12k plus 4. Plus 2 more is 6. Well, 3 certainly goes into the second factor. Goes in 3k squared plus 4k plus 2 times. And then when you do the division, the 3's cancel out, and you get 3k plus 2 times 3k squared plus 4k plus 2. K is an integer. You multiply an integer by 3, you get an integer. When you were in a young grade, you never took a number, say 72, and multiplied it by 3 and got 142.5 or the square root of 7. You always got an integer. This is an integer. You multiply an integer by itself, you get an integer. You triple it, you get an integer. You multiply an integer by 4, you get an integer. 2's an integer. You add 3 integers, you get an integer. When you were in a young grade and you were asked to add, say, 3 numbers, you always, 3 integers, 3 whole numbers, you always got a whole number. You never got like 11.8 or the square root of 13 over 5. So this is an integer. You multiply 2 integers, you get an integer. Okay, so 3 did go into this. Okay, let us look at the next one. It says every integer of this form is also of that form. Okay, so if you have 6k plus 5, if you have a number that's in this form, well, 5 is 3 plus 2. So you can bracket it that way, and you can factor out the 3. This number is on the 3 table increased by 2. It's on the 3j plus 2. Every multiple of 6k plus 5, every number in the form 6k plus 5 can be written this way. Let k equal 7. 6 times 7 is 42 plus 5, that's 47. Well, 47, I want to make sure I write plus 2. So 47 is 45 plus 2. But 45 is on the 3 table. Every number. Now, can every one of numbers in the form of 3? So we did show that 6k being in this form implies that you're in this form. But they claim it doesn't go the other way. 3j being in the form of 3j plus 2 does not imply that. And one way is to think is, you know what, these numbers are generally smaller than those numbers. I can find a number that's less than 5. Like 6 times 0 plus 5 is 5. I can find a number on here that's less than 5. Just let j be 0. Okay, 2 is here. Now, can 6k plus 5 equal 2? Well, the answer is yes, and that's when 6k is negative 3. Because negative 3 plus 5 is 2. Well, if 6k is negative 3, that means k is negative 3/6 or a half. But we don't allow that. We want k to be an integer. So no. I did take a number in this form, and I could not write it in this form. I couldn't write the number 2 in that form. So the answer is no. This is true. It does 3j plus 2 being in the form of 3j plus 2 does not imply you're of this form. But does it imply you're never in that form? I don't think so. If you let j be 3, this is 9 plus 2 or 11. Well, I want to have plus 5. Oh, that's 6 plus 5. So, yeah, this 11, which is in the form of 3j plus 2, is also of the form 6k plus 5. And there are going to be many of those numbers. If you let j be 7, that's 21 plus 2. This is in the form of 3j plus 2. 21 plus 2 is 23. Well, 23 is 18 plus 5. But 18 is a multiple of 6. So this here is of the form 6k plus 5. So sometimes if you're in the form of 3j plus 2, you will be of the form of 6k plus 5, but not always. That's why it says, but not. Conversely, the converse is not true. The converse of 6k plus 5 implies 3j plus 2. Well, converse means just switch these two. 3j plus 2 implies 6k plus 5. This here is the converse statement, but it's not true. 3j plus 2 does not guarantee you that you'll be in the form of 6k plus 5. Okay. Next one says the square of any integer is of this form. Okay, well, in this case, there's three types of integers. 3k, 3k plus 1, and 3k plus 2. We claim that when you square these numbers, you will only be of the form of 3k plus 1. Well, when you square the first one, you get 3 times 3k squared, which is of this form. If you square this one, you get 9k squared plus 6k plus 1. That I just bracketed is a multiple of 3. This is a multiple of 3 plus 1. That's just what we said you can be. Actually, when I said this one, I should have said it was in the form of 3 times an integer. And this last one is 3 times an integer plus 1. This one is 9k squared plus 12k plus 4. Well, think of the 4 as 3 plus 1. Because everything else in that bracket, other than the 3, is a multiple of 3. That is, everything is a multiple of 3 in that bracket. 4k plus 1, plus another 1. Well, this is of this type. It's 3 times an integer plus 1. That proved that one. Using the division algorithm. By the division algorithm, any integer is of the forms 3k, 3k plus 1, or 3k plus 2. And when you square those type of numbers, you only get one of those. Okay. Now they're saying if you cube a number, you get one of those 3. You get 9k, 9k plus 1, and I think the other one was 9k plus 8. This is when you cube a number. Now, we can definitely cube, 9k and 9k plus 1 and 9k plus 2 and all the way up to 9k plus 7. But we don't need to, because if you, let me call these L's. If you cube 3L or 3L plus 1 or 3L plus 2, you're gonna get multiples of 9 plus a remainder. This here is 9, which is 3 squared, times another 3 times L cubed. 27L cubed. This is in the form of 9k. Good. This one, well, you cube the 3L, you have a 1 in front, there are Pascal numbers, 3 times 3L squared times 1, which I won't write, plus 3 times 3L times 1 squared, which I won't write, plus 1 cubed, which is 1. Now, the nice part about this is I have 9s all over the place. 3 cubed is 9 times 3. Don't forget to cube the L. You could ignore the 1. Plus, 3 squared is 9. You have another 3, and you have to square the L. Here, you just have 9L plus 1. Well, I can factor out all those 9s. And I have 9 times 3L cubed plus 9 times 3L squared plus 9 times L plus 1. This is an integer. Call it K. So it's 9K plus 1, which is allowed. Now, what happens when you cube this? Now, you should start seeing a pattern. You're gonna have 9 from the first 3 terms, I guess. You're gonna have 3 times 3L squared times 2 to the 1 plus 3 times 3L times 2 squared plus 2 cubed. You can pull a 9 out from this. 3 cubed is 27, which is 9 times 3. Don't forget the L cubed plus. 3 squared is 9, which I pulled out, times 3 times L squared, times 2, which is 6L squared, plus 9L, I pulled out the 9, times 4, plus 8. This is K. This is of the form 9K plus 8. So I didn't have to use multiples of 9 plus remainders. I use 3L, 3L plus 1, and 3L plus 2. It's a lot easier than to use these 9. How do I know it's 9? 9L plus 7. Right here, 9L plus 8. Right there is 8. They're counting for me. 1, 2, 3, 4, up to 8. And then the last one. So there's going to be 9 of those. You don't want to do 9 of them when all you have to do is do 3 of them, like I did here. That should say cube right there. Now, the next one, the fourth power of any integer is of the form 5k or 5k plus 1. Notice 9 was not prime. They keep talking about 9. So I thought maybe 3 would work. That is 3L plus 1. I meant to say 3L, 3L plus 1, and 3L plus 2. But 5 is prime. How unlucky. So we're going to have 5k to the 4th. We're going to have to look at 5k plus 1 to the 4th. 5k plus 2 to the 4th. And lastly, 5k plus 3 to the 4th. Oops. And let's not forget 5k plus 4 to the 4th. Well, this is going to give us 5 to the 4th times k to the 4th. I'll break off 1 5. So I have 5 times 5 cubed k to the 4th. Which, it'll be easier if I change those letters. There. When you raise an integer to the 4th power, you either get a multiple of 5 or a multiple of 5 plus 1. And here, I'm going to call that L. So, we got 5L. Wonderful. Over here, remember, Pascal's triangle is going to tell us that the coefficients of the 4th power will be those. So you're going to have 1 times 5k to the 4th plus 4 times 5k cubed. And the 1 to a power won't change anything, so I won't write it. Plus 6 times 5k squared plus 4 times 5k plus 1. Well, in each one of these, I can pull out a 5. This one here you could ignore. What will be left over after I pulled out a 5 is 5 cubed times k to the 4th. 5 times 5 times 5 is an integer. K is assumed to be an integer, so k times itself 4 times is an integer. You multiply, you get an integer. Plus 4, I bring out one of the 3 5s, it's in front, so I have 5 cubed, 5 squared, excuse me, times k cubed. Plus here, I have the 6, I brought out one of the 5s, so I have one left, k squared. You want to write this as 100, and this is 30, and this is 125, fine. I factored out the 5, I'm left with 4k plus 1. This is of the form 5l plus 1, which is what I said it might be in. It's one of two. If you notice, all you really have to do is look at the constant, which is 16, which is 15 plus 1. The remainder, this is a multiple of 5, the remainder is 1. Because all the other terms except the constant, we guarantee you will be a multiple of 5. You have 5k to the 4th, there's a 5 in here, plus Pascal's number, 5k cubed. 5 cubed has the factor of 5, plus 6 times 5k all squared, plus 4 times 5k, plus 2 to the 4th, and 2 cubed, and 2 squared, and 2 to the 1, and then no 2's. Either way, they all have a 5. Except the last term. It may or may not have a 5. In our case, it didn't. It wasn't a multiple of 5. So here, when you factor out the 5, over here, you'll have 5 cubed, k to the 4th, plus 4 times 2 to the 1 is 8, times 5 squared, because we factored out one of the 5's, k cubed. 2 squared is 4, times 6 is 24. We factored out one of the 2 5's, we have one left, and we still have the k squared left. We have 8 times k, we pulled out the 5, plus 16, which is 3 times 5 plus 1. Well, I can write 3, and that gives me the 15 plus 1. Ooh, you mean you're in the form of 5l plus 1? Same thing with the next one. Just look at 3 to the 4th, which is 81, which is 5 times 16 plus 1. Again, you're going to have 5k to the 4th plus Pascal's number. Is it 3 or 4? It's 4, of course. Plus Pascal's number times 5k cubed times 3 to the 1 plus Pascal's number, which is 6, times 5k squared times 3 squared. 5k dropped the power of 3 was 1, now it's 2. Plus 4 times 5k to the 1 times 3 cubed plus 3 to the 4th, which is this number. That's important. 3 to the 4th is that number. So we can factor out a 5. We get 5 to the 4th, what we factored out of 5, so we have 5 cubed times k to the 4th, plus 4 times 3 is 12, times 5 squared instead of cubed, because we factored out of 5, times k cubed. Plus 9 times 6 is 54. 5 squared, we brought out 1 5, so 1 remains, times k squared. Plus 27 times 4. You want to work that out? Go for it. It's 108 times 5k. But we already brought out a 5, so times k. Plus 81, which is 5 times 16 plus 1. So this is 5 times L plus 1. 5L plus 1, which is one of the two allowable forms. 5L plus 1 or 5L. What about this one? Well, 4 to the 4, well, that's 4 squared squared, which is 16 times 16, but I don't know what 16 times 16 is. So I'm going to write the second 16 as 4 times 4. I know that's 64, and I actually know what 64 times 4 is. It's 256. Okay, well, 5 goes in here 51 times. That's 255 plus 1 more. So it's going to be 5L plus 1. Because with the exception of the constant, everything else will be a multiple of 5. You're going to have 5k to the 4th plus Pascal's number 5k cubed times coincidentally a 4 to the 1 plus 6 Pascal's number times 5k squared times 4 squared plus Pascal's number times 5k times 4 cubed plus 4 to the 4th, which is 256, which is a multiple of 5 plus 1. Now, I claim for all of this, including the 5 times 51, I can pull out a 5. From here, I'll have 5 cubed times k to the 4th. 4 times 4 is 16 times 5 squared, because I brought out one of the 3 5s, times k cubed, plus 6 times 16, which is 96, times 1 5, because I brought the second 5 in front, times 5 squared, plus 4 to the 4th, the 5 I brought in front, times k, plus 256, which is 5 times 51. I brought the 5 in the front, plus 1. This is of the form 5L plus 1. Use the division algorithm to prove this one. And if I'm not mistaken, that was the last one. Prove that the 4th root, this is somewhat surprising, the 4th power. You take any integer, 2 to the 4th, that's 16. It's 5 times 3 plus 1. It's a multiple of 5 plus 1. You take 3 to the 4th, which is 81. That's 5 times 16 plus 1, which is 81. It's a multiple of 5 plus 1. And of course, if you take 5 to the 4th, well, this is 5 times 5 cubed, which is of the form of 5k. I mean, 5 cubed is 625, which is 5 times 125. It's a multiple of 5. I suspect that's the only time that you're gonna possibly get a multiple of 5. So what if you have 10 to the 4th? Well, this is 5 to the 4th times 10 to the 4th I want to factor out a 5, so I guess I'm mistaken. It's 5 cubed times 10 to the 4th. And this is an integer. 5 cubed multiplied by 10 to the 4th means put 4 zeros. So if it's a multiple of 5 to, if it's 5 to a power or 10 to a power, it'll work. What about 20 to a power? Well, this is 5 times 4. That's 20 to the 4th power. As long as 5 goes into this number, it's going to work. Because I factor out one of the 5s, not 5 cubed. I'll have 5 cubed times 4 to the 4th. So this here is a multiple of 5. As long as I have a multiple of 5, if I have 5 times k to the 4th power, this will be 5 to the 4th, k to the 4th. I can factor out a 5, and then I get 5 times k. Okay, the only way, so if you have y to the 4th is if the form 5k, then y is in the form of 5l. Because if you're of the form 5l, that means y to the 4th is 5l to the 4th, which is 5 to the 4th, l to the 4th, factor out of 5, get 5 cubed l to the 4th, and this here, so let me call this 5m. This here is what I'm calling m. 5m. Okay. That completes this video, which showed some results that are obtained by using the division algorithm. It's powerful stuff, folks. Learn it. If you like videos like this, by all means, subscribe to my channel. If you have a video that if you have a theorem that you want me to prove, put it in the comment section, and if I know how to prove it, I will do so. Leave comments, positive and negative. See you guys next time. Don't forget, watch and learn.